Hello students, welcome to the next session in electrochemistry. Before starting the session, I request you all to subscribe the channel so that you get notification when next part of the video is uploaded. So in this session, we will be discussing how to determine the equivalent conductance of an electrolyte by meter bridge method. So we know that conductance is the power of electrolytes to conduct electric current, or it is defined as the reciprocal of the resistance R offered by an electrolyte solution for the flow of current. So reciprocal of resistance will be conductance, and the SI unit of conductance is Simon. Also specific conductance is defined as conductance of 1 centimeter cube of a solution of an electrolyte. So specific conductance K or kappa K is given by 1 upon R into L upon A. So 1 upon R, that is 1 upon resistance. So the ratio of L upon A, length upon area of an conductivity cell, remains constant, known as cell constant. So from this expression, cell constant will be equal to K specific conductance into resistance R. So the SI unit of cell specific conductance is Simon per meter. So from this expression, if you know the value of specific conductance and resistance of the solution, we can calculate cell constant. Either if you know the value of cell constant and resistance of the solution, we can calculate specific conductance. So a meter bridge is used to find the unknown resistance of the solution. So from the resistance, that is the reciprocal of resistance, gives conductance. So this is the circuit diagram of the meter bridge, in which AB is 1 meter length long wire tightly stretched over a graduated scale of 1 meter fixed on a wooden box, and a sliding contact H is connected to a headphone. So this sliding contact can be slided or moved over the wire. So R is the resistance box and C is the conductivity cell dipped in a solution, that is electrolyte solution taken in a beaker. I is the induction coil for the supply of AC current. So first, during the experiment, the solution is taken in a beaker and a conductivity cell is dipped in it. So now in order to measure the resistance of that solution, a known resistance is removed or unplugged in the resistance box R. Now the sliding contact H is moved or slided over a wire AB. So we can observe that while moving on the wire, at some points maximum sound will be heard and at some point minimum. So gradually it may decrease and it may increase along the wire AB. So the sliding contact H is moved until the sound in the headphone is heard minimum. So that point is noted. Suppose if we use galvanometer instead of headphone, then at this point zero deflection can be observed and the point is called null point. So here if headphone is used, so this is the point at which a minimum sound will be heard. And now the balancing length corresponding to the minimum sound is noted, that is the length of BH and AH is noted, And now resistance of C, that is the resistance of solution C upon resistance R, which is unplugged in the resistance box, will be equal to length BH upon length AH. So from this, resistance of solution denoted as C will be equal to length BH upon length AH into resistance R. So knowing all these values, we can calculate the resistance of the solution. So this is how the resistance of any solution taken in the beaker and dipping conductivity cell we can determine by using meter bridge. Now, while determining the specific conductance of a given electrolyte, first we have to determine the cell constant of the conductivity cell which we are using in the experiment. So determine cell constant, a standard solution of potassium chloride whose specific conductance at a given temperature is known, is used. For example, we can take that standard solution, that is of 0.1 normal KCl solution. It is taken in a beaker and the conductivity cell is dipped. So as said earlier, known resistance is unplugged in the resistance box, and balancing length corresponding to minimum sound is noted, and using this expression, resistance of 0.1 normal KCl solution is calculated. So the resistance of 0.1 normal KCl solution, if it is R, and taking the value of specific conductance of 0.1 normal KCl, we can calculate the cell constant. So cell constant will be specific conductance of 0.1 normal KCl into resistance R of 0.1 normal KCl solution. Suppose at a given temperature, let it be 298 Kelvin, then the specific conductance of 0.1 normal KCl will be 1.289 per meter. So this is the known value. If we substitute for this and resistance R, we can calculate cell constant. And the next step is we have to determine equivalent conductance of a given electrolyte solution. So the equivalent conductance lambda can be calculated using the expression 1000 K upon C, where K is specific conductance and C will be the concentration of the given electrolyte solution. So specific conductance K is needed. So specific conductance K will be equal to cell constant and resistance of the given electrolyte solution. Since cell constant we have already determined, now resistance of the given electrolyte solution is to be determined. So to determine the resistance of the given electrolyte solution, so the solution is taken in beaker, conductivity cell is dipped in it. Again, as we said earlier, known resistance is unplugged and the sliding contact is moved until the sound in the headphone is minimum. So the balancing length is noted corresponding to the minimum sound, that is the point at which minimum sound is heard, and the resistance of the electrolyte solution is calculated using this expression. So once the resistance of the solution is calculated, it is substituted in this expression. So now earlier we have determined cell constant. Now resistance of an electrolyte solution gives specific conductance K. And with the help of specific conductance, equivalent conductance of the electrolyte solution can be calculated. So with this I will conclude this session.